Swayam Prabha. Digital India. Educated India.
So, let us continue our discussions on modal analysis that we had started in the previous lecture. So, today we are going to take yet another example of a system consisting of a bar of varying cross section. So, this is a bar of varying cross section. Consider that A 0 is the area of cross section at the fixed end, and at the free end it is something like A 0 by 4. The field variable is represented by u x comma t, which represents the axial displacement at any point x at any time t. We assume that rho is the density of the material of the bar, and of course, A as a function of x is the area of cross section, and Young's modulus is E, and the length of the bar is L. So, the equation of motion of axial vibrations of a bar of variable cross section may be written as this. The boundary conditions for the system that we have considered are given by the displacement is 0 at x equal to 0, and at the free end we have a dynamic boundary condition, which is a no force boundary condition, which can be written as this. Now, once again we assume a solution form as we had discussed in the previous lecture. So, we consider a solution of this special structure, and if you introduce this solution in the equation of motion, then after some simplification we arrive at the differential equation So, this is an ordinary differential equation obtained by substituting this solution form in the equation of motion, and correspondingly the boundary conditions for this differential equation are given by so this is the eigenvalue problem for our system. So, we have to solve this eigenvalue problem in order to find out the circular eigen frequencies or circular characteristic frequencies omega and the corresponding modes of vibration which are given by the eigen functions of this eigenvalue problem. So, here of course, C is E, the Young's modulus divided by rho, that is C square. Now, for a general variation of the area of cross section, this may not be solvable analytically. So, what we are going to attempt here today is to try to find a class of systems or class of variation of cross sectional area for which this problem might be solvable analytically. So, to see that or to find that class, let us make a variable transformation. Let us consider a new variable W x which is expressed as some unknown function h of x into our amplitude function u of x. Now, if you differentiate, so u prime of x can be written as so this implies now, if you identify this h square, this quantity h square with the variation, the area, then you can eliminate or replace this term with this expression. And if you make this substitution in this eigenvalue problem, the differential equation of the eigenvalue problem, then you can very easily see that this will turn out to be So, if you substitute this u in terms of w in the differential equation and make some rearrangements, then you can write the differential equation of the eigenvalue problem in terms of in this form, and the corresponding so here this is the differential equation in terms of the new variable w. Now, for a special choice of this function h, this differential equation can be written in or can be expressed in a very familiar form or very simple form if h double prime over h is a constant, let us say alpha, where alpha could be a positive or a negative constant. So, for such a class of systems, our differential equation of the eigenvalue problem can be rewritten as now the corresponding boundary conditions can be obtained similarly and which turn out to be so this is our new eigenvalue problem in terms of the variable w. Now, so we are looking at a class of systems for which this function h double prime over h is a constant which is alpha, which may be positive or negative. So, this class of system is characterized by variation of h which may be or which is hyperbolic for alpha greater than 0, it is harmonic for alpha less than 0, and its quadratic h is a quadratic function of x if alpha is 0. So, let us consider certain a particular case that I had shown in this figure. Here the radius is reducing linearly and the area goes from a0 to a0 over 4. So, in that case the variation of the cross sectional area may be expressed as a0 remember that this is h square. So, if this is h square, then H so H is linear in X, and for this situation if you substitute this expression here, then you will find that alpha for this special case is 0. So, if that is 0, then this simplifies further, the differential equation simplifies further, and the solution can be written as so, the general solution of this differential equation is given here. Now, when you use the boundary conditions, so W 0 is 0 would imply H is 0. And the second boundary condition at the free end gives us the characteristic equation. So, which means here, so if H is 0, then W reduces to now if you substitute this expression here at x equal to L, so omega prime is given by minus of 1 over 2 L under root A naught into minus of 1 over 2 L, and so this expression becomes just minus 1. So, from here we obtain here of course 1 over L will remain. So, what we obtain by applying these two boundary conditions is the characteristic equation of our system. So, this is the characteristic equation for a fixed free bar with cross sectional area varying in this form. Now, this is a transcendental equation which has to be solved numerically. Now, a good way to visualize the solution of this transcendental equation is to make a graphical plot. So, so, on the x axis I have omega L over c. So, our characteristic equation is so I will plot. So, I will rewrite this as so the tangent of omega L over c looks roughly like this, and minus of omega L over c is a 45-degree line, minus 45-degree line. So, these two functions are equal at these points, which represent the solution of the solutions of the transcendental equation. So, these solutions are obtained so the first, this point, the first intersection gives us omega 1, which is 2.029 c over L. Similarly, omega 2 and so on. So, you can realize that there will be infinitely many intersections which are discrete. So, there will be countably infinite solutions of this transcendental equation, and for higher intersections you have an approximate solution for n, for high values of n. So, once we have these eigenvalues or the circular natural frequencies of the system, we can find out the corresponding eigenfunctions which describe the modes of vibration of the system. So, these are also now indexed and are given by So, these are in terms of the new variable w. Now, we can go back to our original variable u and write the eigenfunctions So, this is from the structure of W that we had selected. So, W was nothing but So, for our original problem, the eigenfunctions turn out to be these. Corresponding to the eigen values or the circular natural frequencies given here. Now, these eigenfunctions may be drawn approximately here. The amplitude function is or it represents the axial displacement of the bar. So, this is the first mode of vibration with the circular natural frequency given here. The second mode looks something like this. These things can be very easily plotted on the computer and visualized. So, here we find an antinode the node. This is the node at which the solution or the bar. So, this is the point in the second mode. This point does not move in the actual it always remains in its equilibrium position. So, this is the node for the second mode. There is one node in the second mode and no node in the fundamental or the for the eigenfunction u1. So, this node, as we discussed in the previous lecture, is the point on the bar which remains stationary at all times. Next, let us consider a system, a continuous system which is interacting with a discrete system. So, as an example, we consider a uniform bar fixed at one end and attached to a simple harmonic oscillator in this manner. So, here we have a discrete mass represented by capital M and a spring of stiffness capital K, which is attached to a bar of length L this kind of systems are quite common when we have to put absorbers, for example, on a vibrating continuous system or a vibrating structure. So, this example is one such system in which we have a continuous system which is a bar in axial vibration with a discrete oscillator attached. So, we will call them as hybrid systems. So, because we have both continuous as well as discrete systems in this example. So, the equation of motion, or now the equations of motion, because we have a bar and an oscillator. So, we have two equations of motion. For the bar, the equation of motion can be written directly in this form, where c square is E over rho. For the oscillator, the equation of motion can be easily written so y measures the displacement of the mass m from its equilibrium position. So, as you can realize, we have two dependent variables. One is the field variable u, function of x and time, and the coordinate of the discrete mass m given by y. Now, the boundary conditions for this bar can be easily written. So, u at 0 for all times must be 0, it is a fixed end. On the right end of the bar, we have this oscillator. So, we have a dynamic boundary condition So, this must be the force exerted by the spring at this end. So, these are the two boundary conditions for the bar. Now, as I mentioned, this system now has a field variable for the bar and a coordinate of this and the coordinate of this discrete mass m. So, we can represent these variables as a vector and search for solutions of the form this, as we had done before. Now, it may be mentioned that this vector that we are representing it represents the configuration of the system in a dimension which is infinity plus 1. Infinity because of this bar, as we already know, and plus 1 because of this discrete system. So, the modal space is of dimension infinity plus 1. So, if you consider a solution structure like this and substitute in the equations of motion, then you can immediately obtain So, as with the structure of solutions that we have been assuming, we are searching for solutions of this form, we have synchronous motion of the bar and the discrete mass. well, all points of the bar and the discrete mass. Now, so these are the equations that we obtain after substituting the solution in the differential equations, and the boundary conditions tell us u at 0, capital U, the amplitude function at 0 must be 0, and if you substitute this structure here and simplify, we obtain the condition at the right boundary in this form. So, here I have used this equation to simplify the structure of the boundary condition at the right end of the bar. So, our eigenvalue problem now is described completely by these equations and the boundary conditions. So, this is what we have to now solve. Now, the solution of this differential equation may be represented in this form. And if you use the boundary conditions, so the first boundary condition, for example, directly implies C, capital C is equal to 0. Now, if you this therefore becomes simply S times sine of omega x over c. Now, if you substitute this in the second boundary condition and simplify, then it can be checked that we obtain this condition which is the characteristic equation of our system. Now, again this is a transcendental equation which has to be solved numerically. For the eigen values omega. So, you will have discrete solutions of this transcendental equation, but infinitely many solutions exist. So, you have countably infinitely many circular natural frequencies of the system obtained by solving this transcendental equation. And corresponding to these eigen values or circular natural frequencies, you have the eigen functions, the corresponding eigen functions for the bar, and corresponding to these eigen functions you can now find the amplitude function for or amplitude of the discrete mass. So, this is the amplitude function for the bar, and this is the amplitude, the corresponding amplitude at the kth mode for the discrete mass. Therefore, the general solution may be represented by superposing all these solutions in this form. So, this is the general solution for the system. So, you can see that the motion of the system is taking place in a modal space which is of dimension infinity plus 1, and as we had visualized in the case of string, for example, the motion of this bar with a discrete oscillator is nothing but motion of a point in this infinity plus 1 dimensional modal space or configuration space of the system. Now, we can have two special cases which follow immediately from the analysis that we have performed. One is when the stiffness of the spring connecting the bar and the discrete mass tends to infinity, which means that the discrete mass is rigidly attached to the bar. In this case, so it immediately follows from this characteristic equation by taking k tending to infinity, the characteristic equation simplifies to this, and of course, so you can find out the circular natural frequencies from this characteristic equation and the corresponding eigen functions now only of the bar. Is given by this. So, the discrete coordinate, the coordinate of this discrete mass becomes same as, so u, so y is nothing but u at L. The second special case is when this mass becomes infinity, m goes to infinity. So, in that case the system simplifies to this. So, this is the end of this bar is connected to a spring which is attached to a rigid wall. So, in this case the characteristic equation simplifies to this form, and the eigen functions, corresponding eigen functions are again of the same form. In this case, of course, this the motion, since the motion of the mass vanishes, so y t becomes 0. Now, if you look back in this example, what we have discussed, and if you see this eigenvalue problem, You see this boundary condition here is dependent on the circular natural frequency or the eigenvalue itself. So, this system, in this system the boundary condition is a function of the eigenvalue. So, to summarize, we have discussed today two further examples for which we have performed the modal analysis by solving the eigenvalue problems, and we have considered a bar with varying cross section, and we have solved a class of problems for which we have obtained analytical solutions, which we will compare against solutions obtained by other methods later in this course. The other thing that we have discussed today is a continuous system interacting with a discrete vibrating system. So, we will continue this discussion further in the next lecture. So, this completes today's lecture.